Alright guys, so let's talk about mass spectrometry. So basically, unlike other spectroscopy techniques that we're familiar with like the UV, the IR, mass spectrometry is different. This one is spectrometry, not spectroscopy. So spectrometry involves the bombardment of high energy electrons into a molecule, but spectroscopy involves the use of light, absorption of light basically. So infrared spectroscopy gives information about the functional group in a molecule, but it tells little about the size or of the molecule or its the heteroatom that are present. So to determine the structure, we need a molecular weight and molecular formula, right? So mass spectrometry basically differs fundamentally from other spectroscopic techniques. So spectroscopy, I've said this earlier, so spectroscopy involves the use of light, but spectrometry does not. So let's see the next part of it. So in mass spectrometry, a sample is struck by high energy electron, causing the molecule to be broken into fragments, right? So you can think of it as you shooting a box with a gun and then weighing all its weight, right? So this sounds familiar, right? So let's see this. Let's say we have a box. This is a box, right? Let's say this is a box, or let's just any shape, right? So and you hit a gun into it, right? So it's going to be broken into fragments. We are going to have smaller fragment of it, different fragment of it. So this weight, we believe that weighing everything here should give like this weight of this particular substance here will be seen on the spectra of mass spec. So it's like shooting a gun, shooting a box, right? So let's see the next thing here. So so basically mass spectrometry ionizes a molecule in a high vacuum bombardment. So mass spec, the first thing you do, you ionize a molecule in a high vacuum by bombarding it with high energy electron. So the next thing, then you sort the ions according to their masses, and then you record in the mass spec. So basically, ionization, the neutral molecule M is bombarded with high energy electron E. So this causes the ion to be produced. So when the molecule loses an electron, right, it becomes positively charged. I'm going to explain this with the example below. So we have this example. Let's see the ionization of methane molecule. So this is methane. Methane is C, hydrogen, 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 hydrogen. So all the bonds here are considered to be, let's put them as this and this. So this and this, right? This and this. So this and this. So these are what forms the bond. So when you bombard this with high energy electron, like electron here, so what you're going to have, you're going to knock off an electron. So basically this bombardment knocks this electron off. So it knocks this one off, and then you are left with C, hydrogen, this double bond hydrogen. We have hydrogen here again. So this one we have this box here, but we've knocked off an electron. So we have this, right? So this is what is left, and so we always represent this with positive and the radical. So this is like a radical cation, right? Radical cation. So we also call it what do we call it again? So we also call it let me check here, I've forgotten. So yeah, we call it molecular ion, right? So this is an example that we just did here. So radical ion is different from carbocation. Yeah, you need to know that it's different from carbocation. So most carbocations have 3 bonded carbon atoms with 6 paired electrons in the shell. Let's see carbocation. So basically this is a carbocation, right? This one, this one, this one, and here is empty, right? So this is a carbocation. It has 6 electrons, right? So but a radical cation has 7 electrons. So it has 7 electrons and 1 radical. So it is important to note that radical cation is also molecular ion. I've said that just now. So it has the same molecular mass as the parent as a parent sample or neutral molecule. So let's say this box that we just used here, the illustration of the box here. So let's say this box was actually 60 gram per mole, right? So and you gun this. So when you gun, there's an omission in this illustration of a gun. When you gun this box, right, the first thing you have is to have this box, this same box, right, and then you now have an electron that is knocked off, right, before you now have this one, right. So this one is regarded as the molecular ion. This is regarded as the molecular ion, right. So this molecular ion is also the same in mass as the parent box, here. So it's also the same thing as this gram per mole. So it's important to note that this radical cation has the same mass as this methane, the neutral molecule here, right. So that's just what is there. It's important to note that. So let's see the next thing here. So basically, another thing that takes place is fragmentation, actually. So aside the fact that bombarding a molecule with high energy electron leads to the production of ions, so the molecule can also be broken into fragments when bombarded with high energy electrons. So let's see the bombardment of ethane with high energy electron. So basically, the bombardment of ethane, let me cancel this, let me pull this here. So so bombardment of ethane. So basically, ethane is C, and then we have hydrogen here. We have hydrogen here. We have hydrogen. We have hydrogen. We have hydrogen, and we also have hydrogen. So when we bombard this methane, when we bombard it with electron, right? What you have first is this. You have a radical cation, which is also the same thing as the molecular ion, right? So you have this C, right? So this bond here, this is simply like a a dot, right? So you have this hydrogen here. So but this one of the bond here has been knocked off. So even if you write it this way, you have to like specify here that one of the electrons has been knocked off, right? So this is basically a molecular ion. It's also the same as the radical cation, right? So that is that there. So that's the bombardment of ethane, right? So we are setting the pace for something bigger. So separation of ions of different masses. So after ionization and fragmentation have occurred, different mixture of the ions are produced and separated and detected. So basically, remember the illustration of the box. Let's bring it back to that. So we have the illustration of the box. So we said when this is bombarded, right, we have radical cation or the molecular ion, which therefore we therefore now have all these fragments, right? So all these fragments are separated according to their molecular mass. So it's then what we see on the mass spectrum. So let's say this is the mass spectrum, and let's say this is the one of higher mass. So we're going to see it at the far left side. But looking at this, when we bombarded this molecule, right, we have a radical cation. So this is the molecular ion. That's the first thing we should see on the spectrum. So let's say it's 60 gram per mole, right? So this is the mass we're going to see first at the latter part of the spectrum. So therefore, we now see them according to their masses. Let's say this second, let's call this A, let's call B, C, let's call this D. So this is A, right? So we're going to see the next one, B, right? According to masses, C, right? We're going to see D and all of that. So this is increasing masses, right? So so basically, separation of ions into different according to their masses occurs also. So let's see the next thing here. So now let's talk about the mass spectrum itself. Let's talk about the mass spectrum. So the mass spectrum of 2,4-dimethyl pentane is this. So we have the mass spectrum of 2,4-dimethyl pentane. So this is the structure of 2,4 dimethylpentane, right? So let me write it out again. So we have it to be CH3. Okay, let me write it in our board A. So we have this to be dimethylpentane. So 2,4 dimethylpentane, right? Sorry, there's no space here. Don't put a space there. So pentane is, we have 5, 1, 2, 3, 4, 5, right? And so 2,4, we have 2 CH3, we have 4 CH3, and the rest are hydrogens, right? So hydrogen, 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 hydrogen. So this is basically 2,4 dimethylpentane. So let's look at the structure there. So basically, looking at this spectrum, right, we have this. So the first thing we see here is the molecular ion, which is the M plus, or molecular ion or radical cation, right? So we see this M plus here. So if you look at is at the point of 100. So let's see the molecular mass of this. So this is basically everything here is we have it to be, let's write it out again, CH3, CH rather, and then we have CH3, we have CH2, right? We have CH3, and we have H, and we have CH3, right? So let's calculate the total mass. So this one is 15, this one is 12, 13, and then 15, that is 29, this 12, 13, sorry, 13, this one is 13, and this one is 15, that's 28 rather. So this one is 14, this one is 28, this one is 15. So let me punch my calculator. So when we add everything together, we have just hold on, I'm trying to punch it in the calculator. So we have 15 plus 28 plus 15 plus 14 plus 28 plus 15. So everything here is 30, 45, 15, 28, 15, 14, 28, 15. So everything here is 115, right? Let's see if I'm right. So basically what we have here, I think I probably am wrong, so but we can find that out. So but basically the molecular ion peak here corresponds to the total mass of the structure, right? Correspond to the total mass of the structure. So basically I just checked it again, sorry, I was adding this and then still adding this. So basically everything should give you 100 gram per mole, right? So now looking at this structure here, so we therefore have that this is 100, so the molecular ion is 100, right? This 100. So it's telling you that when we bombarded it with high energy electron, it ionized an electron out, and so the molecular ion is this, right? So we have different spectrum, different charts for different fragments of this structure. So basically when you, let's see the structure. So this is the structure, right? So you can fragment it here. We are going to talk about it later on in this video, but when you fragment it here, you remove this, right? That's minus 15 from the whole structure. You are left with 85, right? So that's what we have as the peak here. So when you fragment, different fragment can fragment in different ways. We're going to see that fully in subsequently. So basically the molar mass is 119 gram per mole, right? And that's why we have the molecular ion here, because when you bombarded this with high energy electron, it's basically going to give you a radical cation, which is plus dot, right? So and that's what we see as the 100 gram per mole. It's the same thing as the neutral molecule in terms of mass. So note that the base peak, so base peak does not necessarily correspond to the molecular ion peak. So this is the molecular ion peak, and this one, the highest peak here, is the base peak, right? The highest peak here the one with 100 is the base peak. So base peak does not necessarily mean a molecular ion peak, and we don't always see that because this is a molecular ion peak it should be the base peak. No, we don't see that. So molecular ion peak gives the mass of the sample molecule, right? So base peak is just the strongest peak, the ion with the highest abundance. It is usually assigned a value of 100%. So this is it here, and the intensity of other peaks are reported as a percentage of the base peak. So let's see the next stuff there. So now let's look at this, the isotopic peaks, right? So isotopes have different masses. Isotopes. So mass spectrum can easily highlight the peak associated with multiple abundant isotopes like bromine, chlorine, and all of that. So recall that we said that the molecular ion peak gives the molecular mass of the sample, and it's always the farthest to the right of the spectrum, right? So it's important to note that this statement is not generally true. It is only true for monoisotopic elements. So let's look at this table below. So here is a table, substances containing different isotopes, right? So what we just explained is that we already said that this is a sample, right? And when you bombard it with high energy electron, right, it gives a radical cation, right? So this is the radical cation. Radical cation is also the same thing as the molecular ion, right? So we call this the molecular ion, and it has the same molecular mass as the parent matter, right? So if this is 100 gram per mole, this also will be 100 gram per mole, right? That's what we're trying to see there. So basically, and we also say that this is the mass spectrum, right? We should always see the molecular ion peak at the farthest end, right? So but we're not trying to say that compounds or substances that have different isotopes will not always agree with this. Like the molecular ion peak will not always be the farthest. Sometimes if it's a substance with different isotope, we can always have some peak also here, farthest part here. So but don't worry, we're going to explain that better now. So let's look at the table here again. So basically hydrogen, it has just this abundance. Carbon can be carbon 12 and 13, and this can be, but these are the most important parts that you really need to pay attention to. So sulfur, chlorine, and bromine. So it is important to note that M plus 1, M plus 2. Let's look at that. So let's say we have a peak here. This is the molecular ion peak, right? So we have M plus, we can have M plus 1, and we can have M plus 2. So this corresponds for substances having isotopes, right? So this is M plus 1. Let's say this is M plus, this is M plus, right? This one is M plus 1, right? The third one is probably is M plus 2, not even probably. So this is M plus 2, right? So this is how they are. So like the molecular mass plus 1. If the molecular mass is 100, this one will be 100 in gram. This is mass at the bottom here, mass per charge. So if this is 100, this one will be 101, and this one will be 102, right? So for substances having isotope, that's what we're trying to see. So now looking at this that we highlighted here, so sulfur, the ratio of sulfur and its isotope are just like this. We're going to come into that in further explanation below. So but it is important to note that chlorine does not have M plus 1, right? Now if you try to look at this, the percentage abundance of its M plus and M plus 2 are like 3 ratio 1. So just know it 3 ratio 1. So one way to identify that the spectrum is containing chlorine is that if the M plus 1 is this, let's say this M plus, that is the radical cation or the molecular ion is this, then the M plus 2 will be like 1 ratio of this one. If this one is like 30%, you know, this is abundance, right? If this one is like 30%, this one will be like 10%, right? So this is like the ratio. So anytime you see n plus and you see n plus 2 and their abundance are like 2:1, you can easily tell that this compound is containing chlorine. But we'll see furthermore how we can actually like use this. So that is that one there. So now let's look at a typical compound with no sulfur, chlorine or bromine has a small n plus 1 and even n plus 2 peak. So like if the compound does not have chlorine, sulfur or bromine, the stuff will be so small, like the n plus 1 will be more higher and the n plus 2 can actually be like this, very small. They are not noticeable, right? So but so if a compound contains sulfur, right? Let's say the compound contains sulfur, the n plus 2 peak is larger than the n plus 1, about 4% of the n plus 1. So looking at this structure, so this compound contains sulfur, right? So this is the molecular ion peak, this is the molecular mass of the structure, 76. So looking at it here, this n plus 1 is like let's say 1%. This one is like 4%. Like the ratio of this and this are basically like 4:1. So about 4% of the n plus. So basically, okay, let's put it this way. Basically, this n plus, if the abundance of this is like, let's say the abundance is let's say 40%. 40% is the abundance here. Let me write it here. So the abundance of this molecular ion peak here is 40%, right? This one will be 4% of this 40%. So probably like 4%. So that's just that. But we'll see how we can use it in further explanation. So if chlorine is present, let's say chlorine is present, the n plus 2, this is n plus 2, is about third as large as the n plus. So this is n plus, right? This is n plus 2. So it's always like 2:1. So if this one is like 30%, this one will be 10%. So we'll consider this, we'll look at this. So 2:1. So that's that one. So let's see some more. Now let's look at bromine. So this is bromine, right? So if bromine is present, n plus, this is the molecular ion, and the n plus 2 ions have about equal abundances. So look at this, they are almost like the same. So anytime you see the farthest peaks having the same with its n plus 2, definitely you can tell that this compound contains bromine, right? So that's that. So now let's see another one. So let's see iodine. So this structure I obtained it from this particular website. So iodine is recognized by the presence of iodine ion. So anytime you see a spectrum like this that has a peak at 127 like this, just note it. Anytime there's 127, just know that it's containing iodine, right? So but this is not to say that you should start cramming all these values, no, but we're going to see how we're going to use them. So just try to recognize this, the recognizable elements in the mass spectrum. So bromine, the n plus 2 of bromine is as large as its n plus. So chlorine, the n plus 2 is third as large as the n plus. So iodine, n plus at 127, and then there is a large gap. So looking at what we saw here the other time, so looking at it here, this is 127, right? And then there is a large gap. There are a large gap, no observable peak here. So that's what we're seeing there. So let's move on. So when the molecular ion, like neutral molecular ion, when it is odd, neutral molecular ion, when it is odd, then it's most likely containing nitrogen. So, and you can also try to know this, but this is not really necessary some of the times. So but let's move on. So the next thing now, so I'll just give you as a practice. So point out which of the spectra below indicate. You can also send your answer, just drop your answer to the comment section. I'll try to look at them. So point out which of the spectra below indicate the presence of sulfur, chlorine, bromine, iodine. So looking at this, these two are almost the same. You can tell that this is bromine, right? So looking at this also, this 127, you can tell that there is iodine here, and there's also a large gap here, so you can tell iodine is there, right? So let's look at this also. So I'll give you this to figure out, but look at this, the percentage is like 35 and this one is like 15, so the ratio is basically like 2:1, and that should tell you that chlorine is here. So but I'll give you two, so I'll let you find out this last one. So just send your answer to the comment section. So the next thing is the fragmentation pattern, right? So now let's look at this carefully. Fragmentation pattern. So the mass spectra of alkanes. So basically let's study it with hexane, right? So let's look at hexane, the mass spectra of hexane. So let's draw it here. Let's have a new canvas. So we have hexane, right? This is hexane. So hexane is CH3, CH2, CH2. We have CH2, right? We have CH2, and then we have 1, 2, 3, 4, 5 CH2, and then CH3. So the first thing that happens is that this neutral molecule is bombarded with high energy electron. So what then you have is you have this whole structure here: CH3, CH2, 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 and CH3. So this whole structure here gives radical cation, right? That is the molecular ion. So if, let's see, so if the molecular mass is 86, right? So this one is 86. This is the neutral molecule. So the molecular ion also will be 86 gram per mole, right? Or 86 mass per charge. So this is the molecular ion. So now fragmentation can now occur. So fragmentation is what gives different spectra here. So we have 86, we have a spectra at 71. So basically, for you to know what is lost there, so for the spectra at 71 is basically like let me see if I can write in a better place. Let me see if I can write here. Okay. So this spectra here, looking at this spectra here, we have 71 here. For you to know what was fragmented, let's look at this structure. So the whole structure is 86, and then we have 86 minus 71. That gives you 15, right? So 15 corresponds to CH3, right? 12 plus 3, 15. So it's basically telling you that fragmentation occurs here, right? So give CH3, CH2, 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 right? Give CH2 and then plus CH3, right? So the positive part is what you see on the mass spectrum. The positive part is what you see. So this one is 71, this one is 15. You don't see this one. So this is what you see, and that's what we see here as 71 here, right? 71 here. So for you to obtain 57 is like 86 minus 57. That gives you 29. So 29 is 29 will be CH3, CH2. Let's see, this one is 15, this one is 14. So that's 29. So a tie group is lost, right? So we can write it this way. This is the restructure, right? This is the molecular ion minus CH2, CH3, or you write it as molecular ion minus 29, right? So that's that. Or you simply, but I prefer this though. So you have that one there. So it can break here. When it breaks here, you have 71. When it breaks here, you have 57, right? So when it breaks here, what do you have? When it breaks there, you have 43, and then you have 29. So that's basically that one. So yeah, that's basically that one there. So the next thing you need to look at, let's see another example. So we have 2-methyl pentane. Let's write it out on a plain canvas. So 2-methyl pentane, right? So this is basically like pentane is 1, 2, 3. Let's write it in a better way. CH3, CH2, 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 CH3, right? So this is basically, we have CH3 here. So 2-methyl, that is this, right? So the first thing you need to do is this. The first thing you do here is this. You can fragment it here. If you fragment it here, you have the whole structure here. If you fragment it here, you have the whole structure. You can fragment at any point to give a spectra, but they give when you fragment it at different points, they give more different stability, right? So looking at this, let's look at this structure here. So the fragmentation of this branched alkane commonly occurs at the branched carbon atom to give the most stable carbocation. So basically, you can fragment anywhere to give different spectra on the chart. But for you to, in a case like this, if it fragments here, right, we are going to have CH3 and then CH2 plus CH2, 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 CH3, right? Yeah, plus it's this one now will not be detected. That's one of them, right? So it can also fragment, like let's give this 2. Let's say it fragmenting here and here is the same thing. Let's say it fragments here. So we're going to give CH2, CH3, CH3, right? And the other side will be CH2, CH2, CH3. So this one can take the positive and the radical. And we can also have another situation whereby this one will take, whereby we have CH3, CH2, CH3 as well, whereby this one takes radical and then this one takes the positive, right? CH2, CH2, CH3. But it's important to note that in a case like this one here is given, like the carbocation here is secondary, right? For this one it's 2 degree. For this one is also like this one is 2 degree, and for this one is just primary. No, we only detect the positive, right? So this one here is primary, right? So the order of stability of carbocation tertiary are more stable than secondary, and secondary are more stable than primary. So this is secondary, this is secondary. They are sorry, this is secondary, this is secondary also. They are more stable than this particular one that is just primary. So the peaks for these more stable ones will be higher than this one. So this should give the base peak. This should give the base peak, right? This is secondary. Even though this is secondary, it's not as long as this. So this will give the base peak is most stable of them all. So that is that one there. So let's see. Let's see more. So let's see. The next one is alkyl halide, right? So alkyl halide can actually fragment in 3 different ways. So loss of halide, loss of HX, and loss of the alpha cleavage. So let's see the fragmentation pattern of alkyl halide. So we have alkyl halide. Let's see an example. So let's say we have this alkyl halide. Let's say we have CH3, CH2, CH3, sorry, CH2 rather, and then chlorine, right? So this is an alkyl halide. So we say that the first fragmentation pattern that can occur is loss of halide. So this can actually fragment to give when we bombard it with high energy electron, right, we're going to have molecular ion that will give you this this, right, and then fragmentation therefore occur. So if this one breaks off, we're going to have CH3, CH2, CH2, right, and then you have positive, and this part you have it to be plus Cl radical. So this one is detected on the spectra. So that's one part of it, that is breakage of the alkyl group. So we can also have the second one here, which is loss of the HX group. So we can have loss of this. So basically what happens here is that we're going to have, so it's going to be loss of the hydrogen allied group. So that's just going to be we're going to have this going to be, so let's use this one still. So in that case here, this, let's call this is the alpha carbon, because it's the carbon that is attached to the functional group to this. So this is the beta. So in this second case, what was the name again? Loss of HX. So loss of HX. So the first one occurred at the alpha point. The second one will occur between the alpha and the beta. So we're going to cleave here. So when you cleave here, you're going to have CH3, CH2, right? So basically, okay, let's do it this way: CH2, CH2, Cl, right? When you bombard this with high energy electron, it's basically going to give you radical cation. But this radical cation, most times they are written at the point of functional group here. So you can write it this way: CH3, CH2, CH2, and then this we have a dot plus Cl, right? So now when you are breaking this bond here, when you break this bond here, basically what we are going to have is that it's basically this, right? This is what forms the bond. So when you break it, this one becomes CH3, CH2 radical, and this one will not be detected. Plus we're going to have the other one right here. We're going to have CH2 and Cl, right? So basically this one becomes double bond here. This becomes double bond. Or let me see a better way to explain this. Yeah, let's just hold on this. Let's hold on this. I will explain this better further. I will explain this better. But the third one is alpha cleavage. I think we've talked about something similar. So let's move on. Let's leave this for now. So we'll come back to it. So fragmentation of alkanes, basically alkanes are also like okay. So alkanes rather. So let's say this is an alkane, right? Let's say this is an alkane, right? So basically we have the beta cleavage. So let's add more to it. Let's add more C H H H H A, right? So let's look at this from your notes here. Sorry. Let's look at this. Okay, so I'm trying to open it here. Alright, so basically alkanes, the molecular ion peak for simple alkanes are often very visible, right? So the most common fragmentation is the cleavage of the allylic bond. So basically this is an alkane, right? This is the double bond, and we'll call this, let's say this is the alpha carbon, this is the alpha carbon, this is the beta carbon. So it occurs at this beta carbon or in between of the two. So there's a breakage here, right? And therefore you have this fragment to be dot, and this fragment to be the carbocation. So yeah, so let's continue. Let me try to see other aspect of this note. So that is that one. So another fragmentation that can occur in alkane is the McLafferty rearrangement. So let's say we have this here. So this, let's talk about the McLafferty rearrangement. So basically, for McLafferty to occur, there must be gamma hydrogen, and I'm going to explain that. Normally we have this is an alkane, right? This is an alkane. So the let's look at this structure here. So we label this as the alpha, this as the beta, and this as the gamma, right? So let's see now. So this, we'll call this as the alpha, we'll call this as the beta, but there's no gamma here. So this particular one cannot undergo McLafferty rearrangement because it does not have gamma hydrogen. But let's say we have C. So we have this one to be hydrogen. So let's say we have this again, double bond, C, hydrogen. So let's say this is alpha, let's say this is beta, let's say this is the gamma, right? So there's gamma hydrogen here. So this one can undergo McLafferty rearrangement. So now let's look at the structure that you have here. So I'm going to draw this structure. This structure is this here. So we have CH2, right? We have double bond, we have C, we have CH2, right? We have CH2, and we have CH2, right? So this one is 1, 2, 3, 4 hydrogen. So this one is CH3 rather. So this is the structure that we have here. So now let's see how it can undergo McLafferty. So if you call this alpha, right, and you call this gamma, beta, right, and you call this gamma, right. So how does McLafferty occur? This is alpha hydrogen. So basically, there's going to be cleavage of this bond. So you are going to have, the first thing you have is that you have this bond here breaks or simply moves here. So this one breaks, right? The one between A and B breaks, and you therefore have like you have this CH2. Let's write the hydrogen. This is the alpha. This is the gamma hydrogen, right? So we have this one CH2. We have this one CH2. We have this one CH, and we have this one CH2. So let's see if the structure is the same there. So yeah, the structure is the same there. So basically, you can actually bring this here, but let's see this way. This one here, just simply put it as dot dot. So you have it to be dot and dot here. So when this bond breaks, everything here breaks off, and then you have dot here, and what you have here is dot here also, right? So there's no joint between them. So if this one also breaks off, these are the 3 points that are breaking off. The double bond here is breaking, not moving, it's breaking. This one is also breaking, and the hydrogen, the alpha hydrogen, let's put this through. The alpha hydrogen is also breaking, right? So once this one breaks, you have dot dot, right? Once this one breaks, you have dot dot, and once this one breaks, dot dot. So what you need to look at is that this dot and this dot, they join together, right? This dot joins to this dot, right? And this dot and this, they join together, right? So basically we are left with this one and this one that joins. We have it to be CH2, double bond CH2, right? plus this one we have it to be CH, right? So this one, this bond here, we have CH2 joining to this hydrogen, so this one can become CH3 like that, right? So we have a CH2 also here, right? So it's already joined to this one, and then we have a double bond here already. So I think the bond is complete now. So this is product of the McLaughlin rearrangement.